Hello, and welcome to Lecture 22 on the topic of dispersion and total internal reflection. Dispersion, spreading out of different colors of light, and total internal reflection, a special case of refraction. In fact, this short lecture is all about two special cases of refraction. So it's very much building on the ideas of Lecture 21. Well, namely the refraction part of Lecture 21. It is definitely a couple of simple ideas, but they do deserve their own attention, hence their own lecture. So let's get into them, all right? So you have two objectives. One is to understand that a rainbow created through a prism is due to different wavelengths of light having different indices of refraction in certain materials, okay? And perhaps you've seen that or you've seen a illustration of that idea. You shine white sunlight into a prism, and then out of the prism comes a spread out rainbow. That is dispersion in action, okay? So our second objective is to understand that total internal reflection occurs when the refracted angle is greater than 90 degrees, or exactly equal to it, but practically usually greater, relative to the normal, okay, as we always measure the refractive angles. And thus, no light actually passing from one material to another, okay? So it's hence the name, total internal reflection. Okay. Well, let's define our key terms, make sense of this figure over here, and get into the examples. Okay, so first of all, dispersion. It is the spreading out of light of different colors. So this isn't spreading of light like diffraction, where all colors are spreading. This is just saying that different colors refract differently. Let me elaborate on that idea. So one way that dispersion occurs is from materials with a refractive index that is a function of wavelength. So think of it as n in function notation like this. So n is a function of lambda, right? Maybe it's linear, right? It's some slope times lambda or something, okay? And we can see here are some fairly real life examples. Let me zoom in on this figure. So along the horizontal axis is wavelength in a vacuum. So you think of that as the true wavelength of different colors, like blue around 400 nanometers and red around 700 nanometers. And then here on the vertical axis is index of refraction. And we have a number of different example curves here for real life materials like borate, flint glass, and quartz. And the idea is that the index of refraction is actually greater for the violet or blue light than it is for the red light. See, it actually goes down, okay? Quartz is fairly linear, but a lot of them have complex curves that are fitted empirically. Okay, but that's the idea. And you would be given these values, potentially given a function, but most likely just told two examples. So for one particular color, you'd be given that point, and then for a different color, you'd be given a different point. Okay, and those in practice would be the indices of refractions for those wavelengths. Okay, so that's the idea of dispersion, variable indices of refraction. Okay, very real life phenomenon, and we'll do a couple of examples of it. But let's get into the other big topic of the lecture, the critical angle. It is the angle of incidence for refraction, so it is a case of refraction, that creates an angle of refraction of 90 degrees. So you have an angle of incidence that leads to an angle of refraction of 90 degrees. And if the angle of refraction is 90 degrees, where has the refracted ray actually gone? Well, it's just now running along in a planar case, just running along the interface between the two materials or between the two mediums. All right? So this type of refraction at or above the critical angle leads to what is known as total internal reflection. Okay, and we'll see that in practice. Okay, that's going to be one of the ideas, and we have more examples that illustrate that. Okay, well, I think we're definitely ready for our key equations. The only key equation we have is for, no surprise, the critical angle and total internal reflection, because there's no really relevant formula for the idea of dispersion. Okay, so here is a great illustration of total internal reflection. Here's an incident ray inside some medium with an index of refraction of n sub a. It's coming up, right? It's going to then pass from one material to another. We know we're going to follow Snell's law or the law of refraction to find out how much the material bends. In this case, NB is less than NA, okay? That means that the light will bend away from the normal, okay? We know that the light bends towards the normal when it goes from lower to higher index of refraction, such as going from air into glass, but if it's going the other way, like glass into air, then it's certainly possible that it's going to bend away from the normal and even bend away from the normal so much that refracted ray is now actually never passing into the air, okay? Instead, in this case, it's going to just run along that interface, as I said a moment ago. It never actually enters medium with index of refraction NB. Okay, that's the idea of total internal reflection. It is the principle behind the operation of fiber optic cables, keeping light trapped and then able to bounce back and forth and take whatever curve the cable takes. All right, so here's the formula for it. Make sure we label all of our variables. So theta with the subscript crit, no surprise, is the critical angle. N sub B is the index for the surrounding medium. That's usually where the light is passing into. Surrounding here, interesting choice of words, but definitely, that could be the, around a fiber optic cable, for example, or around a prism where you want total internal reflection. So it often is surrounding, but in this case, it would just be NB, okay? Just where the light would be passing to. All right, and then N sub A is the index of the incident medium, where the light source is located. Okay, all right, so we got two types of practice problems. Zoom out a bit here. We have problems, simple problems involving the dispersion of refracted light within a material that has a variable refractive index. Okay, so there's a couple of those. Type 2, problems that involve using Snell's law to calculate the critical angle between materials of appropriate refractive index. And by appropriate, I mean that they have to allow for a critical angle, because we'll see that it isn't always possible. You can't always achieve a critical angle. You, in fact, have to meet this inequality where NB is less than NA. If that's not the case, if they're equal, or if NB is actually greater than NA, then you're not going to be able to achieve internal reflection, okay? Now, there's actually one last thing I want to say about where this comes from, because I said that we're using Snell's law, but in practice, we're going to use this equation here. But this equation is very simply derived from Snell's law. So if we start with Snell's law, and then we see that it simply becomes this equation, and we can divide both sides by NA to get the showcased equation, and that's simply by setting theta B equal to 90 degrees, which of course is the condition of total internal reflection. Okay, so it really is directly derived from Snell's law. All right, let's go on to our practice. We'll start with a concept question. So, based off the figure, the refractive index of the prism is higher for what color? Okay, so we could cheat here and consider the graph that we just saw on the previous page and saw that all materials seem to all have the same trend. But what do we actually notice just based on the information at hand? Make sure that you can make sense of this. Pause the video if you need to. Okay, well, if you look here, we can look at the angles, okay? So 45 degrees would be the angle of incidence. And which one is bent more towards the normal? Well, the violet light is, okay? The violet light is bent more towards the normal than the red light. They both have a smaller angle of refraction than their angle of incidence, which makes sense because they went from air to glass or something. So certainly the light should bend towards the normal direction of course being the dotted line. But the violet light bends more towards the normal, okay? So what does that tell us? So we see that the violet light is bent more towards the normal upon entering the prism. Thus, the index of refraction of the violet light must be greater, because greater index of refraction means greater bending. So that's it. We got our evidence, violet light. Okay? All right. Let's do our first numerical example, and our only one for dispersion. So the index of refraction for violet light in silica flint glass is 1.66. And for red light, it's 1.62. So they're not equal, close, but not equal. What is the angular dispersion of visible light passing through a prism of apex angle 60 degrees if the angle of incidence is 50 degrees? Okay, so the idea is that the angle of incidence is 50 degrees. That would be like that angle there. Okay, in fact, let's label it. Right, so there's theta 1, that's the angle of incidence. The light is going to come into the prism. We're going to have theta 2. Then we're going to relate that internal angle, theta 2, to theta 3, using the apex angle, because we have a triangle formed of those angles. Okay, there's our triangle. Okay, we've seen this before. You can see this exact approach in the previous lecture, lecture 21. Okay, just no dispersion in that case. Okay, and then we have the idea that we want to find this angular spread. This is what we're curious about. Okay, so as with other prism problems, we use Snell's law twice, okay, as it goes into the glass and then as it comes back out. And we're going to relate the internal angles, that's theta 2 and theta 3, to the apex angle alpha. Okay, so here's Snell's law the first time, Snell's law the second time, and the relationship between the apex angle and the two internal angles. And again, this simply comes from summing up the sides of the triangle, summing them 180 degrees, and canceling out what we can. And you can see that kind of where that comes from again in lecture 21. Okay, so we then just want to go ahead and just solve for this, all right? So I'm going to say, okay, well, I'm interested in theta 4, all right, that final angle when the light returns to the air, because that's going to allow me to actually calculate for the difference in order to get the measure of dispersion, that actual angular spread, okay? So I definitely interested in theta 4. So I set that up, okay? So I initially solve it in terms of theta 3 by just using Snell's law, but then I do a substitution and get rid of theta 3, because then I can define that in terms of alpha and theta 2 because of this relationship here, okay? Now I know alpha, but I don't know theta 2 yet, okay? So what I'm going to do is replace theta 2 with this expression. See what I've done? I've literally just replaced that whole theta 2 with this inverse sign. And of course, that inverse sign just comes from this relationship of Snell's law. So we got this nice long equation by just basically solving directly for theta 4 and doing some substitutions, okay? And of course, we know theta 1. We were told it's, in fact, 50 degrees. So we're good to go. We can just plug in our known values and solve for theta 4. Okay, now the only thing that's going to differ is going to be the value of N2, see? Because N1 is always going to be air, but N2 is going to be different for the two colors of light, all right? It's going to vary between 1.66 and 1.62, okay? So for red light, color-coded in red, which of course is the color I typically use, we see I just plug in 1.62. Here, dividing by 1, of course, has no effect. And here it's going to be 1 over 1.62, so there we go. And otherwise, it's just the apex angle and the angle of incidence. And so we then have the final angle, theta 4, the angle at which the light exits the glass prism with this particular apex angle relative to the normal, which is that black line. Okay, now let's do the same thing for violet. All right, this is my violet color here. Okay, just slightly different numbers. Obviously, all I've done here is just replace the 1.62 with 1.66. All right, well, sure enough, we got 63.2 degrees for the violet and 58.6. Totally what we'd expect because the violet should bend more than the red. Right? The angle for the violet should certainly be larger. That definitely tells us that we didn't make an obvious mistake. Okay, all right, so then we're going to go ahead and find the difference between the two because that will be our angle of dispersion, our actual angular spread, and it's 4.61 degrees. Pretty cool. So this is really kind of the most involved thing you can do with a dispersion problem like this, and it definitely illustrates all the key ideas. So I think we're all set to move on to the idea of critical angles and total internal reflection. Let's do a very much plug and chug problem to get us started. Okay, so the index of refraction of benzene is 1.8. The critical angle for total internal reflection at a benzene air interface is what? So the idea is that we've got our benzene down here, we've got air up above, we have light coming in, and we want the light to come up to that interface as if it's going to pass into the air, but instead get refracted so it never actually passes in. In practice, when this happens, you would notice a glimmer of light on the surface of the benzene. That would be kind of the real life manifestation, the messy real physics of seeing total internal reflection. You actually see it kind of glinting or glimmering at the top of that fluid. Okay, so anyway, here is our appropriate formula, and we're simply just going to solve for theta sub c. Obviously, I've just shortened crit to c, and obviously that's going to take an inverse sign. We know our two indices of diffraction, and 33.7 is our answer. Actually, not that steep, right? We don't even have to come in at a very steep angle in order to get total internal reflection. And that's owing to the fact that this is a pretty high refractive index, right, as far as refractive indexes go. Okay, so here's a question for us. Why is there no critical angle at the air-benzene interface? In other words, why can light reflect internally when exiting the benzene, but not when entering it? I mentioned before that that is a rule, but why? Why is that the case? Okay, well, because in this case, NB would equal the benzene, and then we'd have sine inverse of 1.8. Okay, well, if that was the case, it wouldn't work. You can't take sine inverse of 1.8. It's undefined. It's impossible to happen. Light cannot refract that much. Because think about the idea. That would be going from lower to higher. When you go from lower to higher, you bend towards the normal. No amount of bending towards the normal, and lower to higher index of refraction, of course, no amount of bending towards the normal is ever going to get a ray that is running along the surface. You're going the wrong way, right? So it simply can't work. So total internal reflection can only occur when going from higher to lower index of refraction, okay? So like coming up out of the benzene, coming from glass into air, okay? Coming from water into air. Those are all valid situations for total internal reflection. Going from air into anything else? No, because everything's going to be higher than air. Air having a index of refraction of 1. All right, 1. Okay, so let's do one with water. An underwater lamp submerged in a lagoon at night emits light in all directions at a depth of 7.2 meters. An observer in a boat would see a circular region of illumination of what diameter on the surface of the water? So there's a bit to unpack here. Why is there a circular region? What do we mean by that? Well, because there's a certain angle, that is the critical angle, and light at that point never passes out of the water. So that means that that source of light is limited to where you can actually see it in the air above the water. Okay? Because anything beyond the critical angle, no light's getting out. All that light is trapped inside the water. Okay? So here's a picture. Here's our lamp, right? Here's the critical angle, whatever it turns out to be. The idea is that light can take that critical angle, would get refracted along the surface, shimmering, as I mentioned, all right? And if any light rays took a even steeper angle, something like this, then they would get refracted back down into the water. So the water above would appear dark. So then only the water where the light is actually getting transmitted, for example, here, all right? So here the light is actually getting transmitted, only then would the water appear bright to an observer above. Okay? All right, so this is going to be our circle of illuminated water. Okay? And it has some diameter, d. So with NB equaling 1 for air and NA equaling 1.5 for this water, it's higher than typical water. I don't know, maybe it's extra salty or something. Then we're going to solve for the critical angle using the formula, all right? And of course, just do our inverse sine function, and we get 41.8 degrees. All right, excellent, okay? So that's a general result. That would apply to any depth, okay? Because that's just the angular value. So then we want to relate that with a little bit of right triangle geometry to this side of the triangle, okay? So in that case, tangent of the angle we solved for, the critical angle, equals opposite over adjacent. Opposite is d over 2, right? Just half the diameter. And then adjacent side is the depth. So then if we go ahead and solve for d, which will just be 2 times that, right? Then we end up with 12.9 meters. That is the diameter of our illuminated spot of water. Very cool. All right, 2 more to go. Example 4. All right, this one's also pretty straightforward, but it's a neat application of total internal reflection, and that is getting light to take tight turns, like in a pair of binoculars, by just setting up little prisms. So what is the minimum index of refraction for a glass or plastic prism to be used in binoculars so the total internal reflection occurs at 45 degrees? Right, so we want to make sure that if we cut the glass like this, that the incident ray comes in, hits at 45 degrees, and that does what we need it to do, which is totally internally reflect the ray so that we can then direct it where we need it to go. Okay, so what's also different about this one is instead of solving for an angle, we're actually going to solve for the index of refraction. Okay, so we'll set up the same equation, or the same equation, all right? And this time we'll solve for n, all right? We know the critical angle is going to be 45 degrees, and so it's simply a matter of rewriting this, cross-multiplying, solving for n, and finding out that 1.4 will do the job. Now, what if we were using these binoculars instead of in air, where our surrounding index of refraction is 1, what if we were using them in water? Well, that would change things, all right? These would be underwater binoculars. And in that case, what would our prisms need to be made out of? Well, in that case, we'd set this up the same, but now our 1 would be replaced with 1.5. And we solve for n in that case, what the refractive index of the prisms, it's 2.12. Now, this is very high for an index of refraction. Really, only diamonds have index of refractions this high. So we see maybe it's practically not very feasible to make underwater binoculars. Okay, let's do our final example. Not too much new with this example, pretty straightforward, but we are solving for something else. We're solving for the speed of light based on a critical angle. So kind of neat relationship of ideas. Okay, all right, so a thick slab of plastic, right? Here's the plastic down here, lies at the bottom of a tank filled with water. Here's the water, okay? Having an index of refraction of 1.33, that's the water's index. A narrow laser beam is shown directly downward through the water on the plastic. You then gradually rotate the laser. So at first it was heading straight down, and then we rotated it until we got to something like in the picture, thereby increasing the angle with respect to the normal, right? This theta went from 0 to some value greater than 0. You carefully note that at the instant the beam makes an angle of 66.5 degrees, all right, you get, well, no light entering the plastic. Well, we know what that is. That's total internal reflection within the water, all right? But it did enter for smaller angles, okay? So based on the information, what is the speed of light in the plastic slab? Right, kind of neat, right? So we can relate these ideas and actually get the speed, the velocity of the light in the plastic, okay? So of course, what we need to find first is the index of refraction of the plastic based on the information, okay? So it's gonna be this equation here. And by the way, is the index of refraction gonna be higher or lower than water? Because you should be immediately able to say which is gonna be. It's gotta be lower, right? It's gotta be, because otherwise there's no way we could get total internal reflection. If this plastic was like 1.4 or something, then it wouldn't work, right? So we know it's gotta be less than 1.33. Okay, so let's go ahead and solve for it, and we get 1.22. All right, that makes sense. Okay, now we're going to go ahead and then use that index of refraction, relate it to the velocity of light. Okay, here's the relationship between the velocity of light in a vacuum, C, and the velocity of light in a transparent material, V, and the index of refraction of that material. So we simply rewrite this to solve for V, plug in our values, 300 millimeters per second for the speed of light in a vacuum, divide by the index of refraction that we found, and we find out that the light is moving at 246 millimeters per second in the plastic. So slower, all right? Well, there we have it. I hope that this introduction and brief lecture on total internal reflection and dispersion has been both interesting and informative. Thank you so much for watching.